Only the rest of the chapter, we're going to cover the different forms of heat transfer, radiation and conduction specifically, and then we'll start the first law of thermodynamics. So if you just put in on Google forms of heat transfer, you can see three types of heat transfer. Heat is transferred via solid materials by conduction, liquids and gases by convection, and electromagnetic waves by radiation. Okay, so those are the different forms of heat transfer. So the radiation can be radiated through gases or even through vacuum. So we get the radiation of the sun through vacuum space, right? You don't need a material per se, but for convection, you need liquid or a gas. And then for conduction, it's a solid material. So you two solid materials have to touch each other, like my fingers and the table, in order for you to conduct the heat. So so they show you some image here of, so let's say you're talking about the house. Convection around windows and doors. So there's a convection around the window and the door, so the heat comes in, and then you got convection, so heat rises, right? So the idea that the heat is convected in the room, so that's convection, right? The hot air rises and cold air sinks. Then you got the fireplace creating fire, and that is radiation through electromagnetic rays, right? Particularly infrared is what heats you, right? So you get the radiation from the fire, and that's what heats you. Light bulbs give you heat, so that also warms the room, right? So that's radiation. And then you got here convection, hot air is rising. Then you have conduction, so that means the fireplace, the fire gets hot, and because it's in contact with this, you see, so it conducts the heat through any solid material. So now the floor gets hot by conduction. So it's kind of nice to see all of that taking place in one picture: radiation, conduction, and convection. You can see some other images. So it's nice to see conceptual understanding of this by visual. Similar this one, conduction. Let's see, there's a different picture. Okay, same thing here. You got, let's say, you're boiling water. This one is mainly what form? Is there mainly convection going on here? Yeah, the fire is in touch with this. The hot liquid here is rising and sinking. Is there any conduction going on?
Between water and
Because conduction is between two solids.
two solids. There is the bottom and then the parts thing.
Is there any conduction, transfer of heat through conduction going on here? Maybe this metal gets warm,
Yeah.
and then the metal transfers heat to there through conduction,
Yeah,
right? Because it's between two solids. Is there, but how does the metal get warm? The fire, even, let's say the fire does not make contact with the metal, right? So how is this metal getting warmer?
Radiation.
Radiation. I see. So it's kind of nice to see all of that taking place. Oh, when you put this on, see the fire is radiating its heat, making the metal hot, and the metal is touching this pot, making it hot by conduction, and then when this gets hot, the water touching it gets hot by convection, and then the heat rises and the sinks, and that's convection right there. And then that heat that is rising makes the pot hot, and then that transfers its heat through the handle by conduction, you know. And if the handle is metal, you're gonna burn your hand, so that's why you put it rubber, some other material that is less, more insulating, right? So there's all these kinds of things going on, radiation, conduction, convection, even through theirs. Here, same thing. a different picture. Optional lower, so this is a fireplace. The more intricate picture of what's happening in a typical fireplace. So this is a radiant heat, it's heating. Convection air intake. Oh, so you see you need a nice convection for a nice fireplace to do its job. So you need the cold air to enter here and then rise, and then it's in contact with this door, starts getting warm, and then it sends the hot air through here. So you're getting hot air coming through by convection, and then the radiant heat of the glass. Even if you close it, the fireplace, the glass gets warm and the glass radiates the heat. So you're getting that radiant heat and the convective heat, and then what else is going on? The hot air is rising here, exhaust gas, and then you got here outside wall to support it so that the grass doesn't burn, right? And then you're sending this out through the chimney. So nice, all of that, all three taking place right there. And then you can keep on taking a look at other pictures. So all of this stuff is going on a daily basis. Okay, so now let's focus on the radiation first, and then we'll do the conduction. We'll do both of them today. So radiation. So the equation is P is equal to A E sigma T to the power fourth. That's the amount of power that you radiate. Radiation. P is equal to A E sigma T to the power fourth. Okay? So this is known as the Stefan-Boltzmann Law. So you first define what's known as a black body, and it's not necessarily black color, but black color is an example of a black body. These are called black body radiation. So black body radiation. So it's a bit hard to understand first, because we're used to, when we say black, we're used to always referring to the color black. But black body radiation is a concept. So it says, black body, the black body is defined as a body that absorbs all radiation that falls on its surface. You see. So that happens to be, an example of that happens to be a black object, but it's not necessarily just black. So black body is defined as a body that absorbs all radiation. Actual black bodies don't exist in nature, though its characteristics are approximated by a hole in a box filled with highly absorptive material. So we can approximate a black body. It says take a box, put a hole in it, and then the radiation will go through that hole, and all of it will be absorbed by that material if it's absorbent, if it's very absorbent material. The emission spectrum of such a black body was first fully described by Max Planck. Okay, so those of you who are taking the modern physics, you probably covered that topic. A black body is a hypothetical body that completely absorbs all wavelengths of thermal radiation incident on it. Such bodies do not reflect light, therefore appear black if their temperatures are low enough so as not to be self-luminous. Okay, so if they're like basically a color black shirt, color black anything, is not going to radiate enough energy for us to see the luminosity of it if it's not very hot, right? So since it's not reflecting anything, it's going to observe to be black, right? But if we heat it, then it could actually glow in the visible spectrum, even if it appears black. But then we're going to start seeing it radiate red and stuff, right? So that's why the topic is a bit abstract, because we're referring to black objects, then black body radiation, but black color is an example of black body, right? So such bodies do not reflect light and therefore appear black. All black bodies heated to a given temperature emit thermal radiation. The radiation energy per unit time from a black body, which means the power, right, per unit time, that's the power, is proportional to the fourth power of the absolute temperature and can be expressed with Stefan-Boltzmann Law. T to the power fourth A Q is the heat transfer per unit time. Sigma is a universal constant, 5.6703 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth. Right? So it has to be, this one has to be Kelvin because it's not delta T, it's temperature, right? So absolute zero, therefore, can be defined as the temperature at which, if you're that cold, you do not radiate at all, right? T is 0 Kelvin, so no radiation takes place. So you see, there's different ways then you can describe the meaning of absolute zero. At absolute zero, speed of sound is 0, so no sound waves can travel. Absolute zero is the temperature at which no radiation takes place. You don't radiate. And absolute zero is also the temperature at which all molecular motion stops. So the root mean squared velocity of gas molecules at absolute zero is going to be 0. So all molecules stop. So we're going to see that later in chapter 21. Okay? So if something is at 0 Celsius, does it radiate anything? Oh yeah, because that's 273 Kelvin, right? A E sigma 273.15 to the power 4. That's why the 0 Celsius means nothing. It's just a random scale that we have on Earth to indicate the temperature at which water freezes, but you still radiate just normal, like a normal object, right? So then you have here the other possible units for sigma, British thermal unit, hours per feet squared. We're not going to use that much. T is the absolute temperature. Area is the area of the emitting body. So the bigger the surface area of the object, the more area it radiates, the more, right? If area is big, you radiate more power. This has a lot to do with biology too. You know, like let's say certain trees that live in desert places, they barely get enough water, right? Their leaves are small. Okay, why? Because the water barely gets there. They don't want to radiate that away or evaporate that away also, right? So in order to conserve water and not to conserve heat also, the leaves are small, the surface area of the leaves are small so that they don't radiate that away. So you can look at the biological implications of this to all kinds of different species of plants and animals and stuff like that. So basically, that kind of makes sense. The bigger the surface, we radiate away our temperature through the surface area of our skin. So let's see what else it says here. Radiation from surfaces. Heat emission, watts per square meter. And this is the temperature. So at 0, this is temperature degrees Celsius. So at 0 degrees Celsius, you're radiating away, what's the units of this? Watts per square meter. But they didn't give us the area, right? They didn't give us the surface area. I guess the surface area is just anything, some number. The emissivity E, what does that mean? They're not talking about E yet, because they're focusing right now on black body objects. The emissivity of black body is 1. You see? Black bodies. Then they're going to probably mention about the emissivity of different materials. So what's happening when you go from 0 to 200 Celsius? When you go from 0 to 400 Celsius, the power radiated is becoming more and more, right? What happens is, since it's the temperature to the power 4th right? Every time that the temperature doubles in the Kelvin scale, then the power radiated multiplies by a factor of 16, 2 to the power 4, right? So when you go from 0 to 200 Celsius, what's happening? By what factor should the power increase? Well, what we have to do is we say 0 is 273.15 Celsius. 200 Celsius is what? Kelvin. And then 200 Celsius, right, is 473. This is not quite double that, you see? So take the ratio of this and raise it to the power 4, right? Then that's how much you know how much the ratio of the power radiated. So P2 over P1 is going to be T2 over T1 to the power 4. So 473.15 over 273.15 to the power 4. Okay? What is that? It's not quite 2. Nine times more. So that means if the power radiated at 0 Celsius, what was that? Well, we know we can't tell because it looks like this is a log scale. I can't tell what this number is. But whatever that number is, that one should be 9 times more. Okay? That one should be 9. So what is this? 200, 300, 400, 500? What's the scale? It's a weird scale, huh? Well, it looks like something like 500, right? What's 500 times 9? 4,500? Well, that would make sense. 4,500, right? So that would be halfway between here and here. Okay, so then the same thing is happening. When you go from 200 to 400, it's not going to be the same ratio. It's going to be less, right? The ratio of 400 Celsius to 200 Celsius in Kelvin. So it's not going to go up by a factor of 9 anymore. From 400 to 600, it's not going to go up by a factor of 9. So that's why it's kind of like plateauing. Let's see. Oh, now they do the same thing in degrees Fahrenheit.
What is E again?
Yeah, they haven't talked about it yet. So E is the emissivity of the object. So now they're going to define heat radiation from the sun. If the surface temperature of the sun is 5800, if we assume that the sun can be regarded as a black body, the radiation energy per unit area can be expressed by modifying 1. So basically notice, the sun is not really a black color, but they're assuming it can be treated as a black body because it absorbs energy at all wavelengths and emits radiation equally at all wavelengths. So they're treating it as a black body. Then they go to gray bodies and emissivity coefficients, right? So then they're going to talk about other colors. So you see, that's where the epsilon comes in. For objects other than ideal black bodies, gray bodies, the Stefan-Boltzmann law can be expressed as E sigma T to the 4th. And A is the emissivity coefficient of the object, 1 for a black body. Let's see. So for black body, that's why they didn't mention it. E is 1. So for the gray body, the incident radiation, also called irradiation, is partly reflected, absorbed, or transmitted. Let's see. So you see what's happening, the details of that. Incident radiation, that's irradiation, then you got reflected irradiation, absorbed irradiation, and then transmitted. For black body, what would happen? Oh, the radiation would come, and all of it would be absorbed. So all of it, nothing reflected. And see, that's a black body, no reflection. So all of it would come through. But if it's non-black body, such as gray, part of it is reflected, part of it is absorbed, and then transmitted means it goes through the object and makes it through. So the emissivity coefficient is in the range depending on the type of material and temperature of the surface. Oxidized iron, emissivity is 0.64. Polished copper, emissivity is 0.03. Oh, so basically polished copper is the opposite of the black, which means most of it is reflected. You see, emissivity 0.03. So that means most of the energy is reflected rather than absorbed. So emissivity coefficient for some common materials. Then you have the emissivity coefficients. If we click this, okay. Alloy polished, aluminum 0.09, aluminum foil 0.04. So you see there isn't really anything that's zero, but reflecting objects have low emissivity. So 0.04, 0.09, something like that. So aluminum is going to be 0.04. Then you got other materials, asbestos board 0.96. So that looks looks like a black body. Asphalt 0.93. You see? So that's making sense. Asphalt, those are all black objects, 0.93. Basalt 0.72, so different kinds of rocks, right? Basalt rock is more black, so it's 0.72. Black body matte 1.0. Sometimes you see colored, cars are colored in matte colors, right? So that's black body, that's 1.0, everything absorbed. Black lacquer on iron, black parasynoptic, black silicon paint. So you see, you can talk about paint colors. Brass polished, 0.03. So you see the full range of emissivities. Roofing paper, 0.91. Right, that's the stuff that they put on the roof. Roofing paper, 0.91. Okay, so that's making sense. So it's always nice to see numbers and see what they mean. And water has emissivity, 0.95, 0.963. All right, so that's interesting. 0.95, 0.963. So what does that mean? Water absorbs more heat, right? It doesn't reflect too much. So that has something to do very important with how water regulates the temperature of the earth too, right? So since about, what percent, 60% of the earth is water and oceans, that means water absorbs the heat coming from the sun, helps us keep warm. But water's temperature does not rise easily because its specific heat is high. So water is absorbing the heat, but not rising its temperature, you see? So that's very good. It's not like sand where it might absorb and the temperature goes up very easily, right? So water is like absorbing, it's acting like a buffer, and then its temperature is staying more or less the same, you see? So water has a lot to do with climate control, right? Snow would be the other opposite. Do they give snow? Because snow is a different material. So you can kind of look up all this stuff, and it's also related to climatology. Clouds have a certain absorbivity, emissivity. Snow has sand, different materials, and that goes into determining what the temperature of the earth is, what stable temperature the earth reaches. That's why when the glaciers melt, right, snow probably reflects more energy than water, right? When the glaciers melt, it turns into water. Water will absorb more heat, so the temperature of the earth might rise. And so it might be a domino effect. Us causing global warming might cause the glaciers to melt, which might cause more global warming because now we have more water which absorbs more heat. Do you see? So we need a certain reflectivity. We need to reflect some of the energy of the sun, not absorb it all. you see. So you can go into the whole to the whole global warming issue, okay? Let's see, what was I that I mentioned? Okay, now we talk about not only how much energy you radiate, but how much energy you absorb from your surrounding, you see. So you're constantly radiating to your surrounding and absorbing from the surrounding, depending on if you're a black body or a non-black body. If you're a black body, the emissivity is 1, so that means you're a good radiator and you're a good absorber. You see, black objects absorb everything from their surrounding and radiate very well if they're hotter than their surrounding, you see. So, depends. So now look at the equation, the net equation. If a hot object is radiating energy to its cooler surroundings, the net radiation heat loss rate can be expressed as E sigma T H to the 4th minus T cold to the 4th. You see? By the way, earlier I mentioned when we were talking about, what topic were we were talking about, where I talked about this graph, intensity as a function of wavelength. And then I said this is Viens Law, right? And I said when objects get hotter, what happens? The amount of radiation that they do shifts from here to here, right? So when objects get, this is called Viens Law. Lambda peak is 3 million divided by T to the power 4. Not T to the power 4, divided by T, right? So when the object gets hotter, what happens? The peak wavelength of the object gets smaller, right? So when the object gets to be about 3,000 Kelvin, the peak wavelength is what? 3,000 over 3,000. So then this cancels. It's 1,000 nanometers. So the object begins to glow red. So this is a red-looking star. So this is 1,000 nanometers, right? But the objects at room temperature are gonna radiate what? It's going to be 300 Kelvin, right? Instead of 3,000 Kelvin. So objects at room temperature are roughly around 300 Kelvin. Then that's going to be what? 10,000 nanometers. So that means the peak wavelength, what happens to the peak wavelength? It's 10 times larger. And that's the radiation that you and I are doing to our atmosphere. We're radiating 10,000 nanometer range. And that's infrared. Infrared. And then this is red. So now if I make something hotter than 3,000 Kelvin, then you can radiate yellow, Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. Then you have the ultraviolet, X-ray, and then gamma ray. Gamma ray is the shortest wavelength, right? So, so now how is this equation related to what we learned there? Okay, this equation is the area under the graph. It's focusing on the area under the graph. So if I go from 300 Kelvin to 3,000 Kelvin, by how much does the area under the graph increase? Multiplying the temperature by 10, right? 10 to the power 4th is what? Right, so when I go from 300 Kelvin